Hello, relativity friends. A couple of days ago, we were looking at a visual explanation of time dilation, and we were working in what's called Minkowski space-time. Okay, and in that space-time, you're assuming you're far away from a gravitational field, so the time dilation you're experiencing is from velocity. Okay, now we want to look at gravitational time dilation. So there's two types. There's the one from special relativity, which is speed, the velocity you're traveling, and one from general relativity, which has to do with gravity. So a moving clock moves slower, and a clock in a gravitational field also moves slower. And we're going to look at that right now. Okay, I got this idea from my book, General Relativity: An Intuitive Introduction by Ville Hervoven. This is on the Profound the Physics website. I'll leave a link. Okay, before we can go to Desmos and look at this, we need to talk about where it comes from. This is called the Schwarzschild metric tensor, right? So this is the metric tensor in four dimensions: one dimension of time and three dimension of space. And as an example, this is the one we're interested in. This is the GTT component of this metric, the tensor, and that's the one we want. If you want to know where this comes from and how to derive it, it's very interesting. It's a lot of fun. It's also very long. So I'm going to leave a link to Eigen Chris did a marvelous job at this, and you can follow that link at your leisure. Okay, so we want this GTT component of this, which is this. And these constants here, the gravitational constant, the mass of the object, and we're talking about a black hole, so something wicked massive, and the speed of light. These constants we're going to call something the special. This r is the, if this is the black hole, r is the distance you are away from it. Okay, so these constants are defined as something called the Schwarzschild radius, which is the point of no return when you going toward a black hole. Don't go there, kids. Very dangerous. Okay, so GTT is equal to this. And what is GTT? That's just the dot product of the basis vectors, ET dot ET, which is really just ET squared, right? So ET squared is equal to that. We take the square root of both sides, and we'd also first take the absolute value, because taking the square root of this gives us a complex number, and that's unrealistic. We're looking for something real. So we got the absolute value of the ET basis vector is equal to this expression. Now we can go to Desmos. Okay, what do we got here? This I'm in Desmos. All right, we have a black hole, and it looks like one. And this black hole is 1,000 solar masses, so it's 1,000 times more massive than our sun. Okay, and each one of these blocks is 1,000 kilometers. So if you solve that equation, it turns out the Schwarzschild radius, r sub s, is 3,000 kilometers. So it's 3,000 kilometers away from the center of a black hole. All right. Now out here, I have some poor mook who is, what is that? 1, 2, 3, 8,000 kilometers away. And this is their ET basis vector, their time basis vector. Now this is part of a vector called the four velocity, because you're in four dimensions. We're just looking at two dimensions. Actually, we're just looking at one dimension. We're going to travel in one dimension. All right. So this vector can be expressed as a linear combination of its components and basis of a vector. So we're just looking at the basis vector itself. Okay. Now what we're going to do is move that basis vector toward this black hole. Let's see what happens to it. Look at that. Oh, it's shrinking. It's getting smaller and smaller and smaller until it blows up. It can't go any further. Okay? Because of the equation. So, what's that telling us, right? So, every time I move this basis vector, it changes, which means that something is happening to that time component. That time component is getting smaller and smaller and smaller and smaller. Now, This is to an outside observer. There's an outside observer here measuring time as this person is moving toward that black hole. The person here that's traveling, their proper time isn't changing. They don't know anything is going on oddly about this, right? So for an observer, they're seeing time slow way down. For this person traveling, their proper time is unchanged. They don't know the difference. They're going to go right on into this black hole. All right. So I just thought this was a really easy geometrical way to look at gravitational time dilation based on what we've been learning already. Okay? Wasn't that fun? I'll see you later.